library structures and library structure 2. And let's get started. Why Rosetta is set up as a library, and what is a library anyway? And what does that all mean in Rosetta, right? You're like, yeah, what does it mean? So a library is a collection of pre-compiled code, functions, classes, data structures that other programs can use without re-implementing those features. So it's really like almost like modules, but not quite. So basically you have over here, a library is usually a set of header files plus compiled objects. So when you compiled in your homework, you had header files, you had CPP files, and then when you compiled, you had those object files, right? So when you build your executable, the linker links these different libraries together. So when you compile, you basically create the object files, and the linker then links those object files together. And let me explain this a little bit in conjunction with Rosetta, right? So the reason why Rosetta has different libraries is because at some point the code became too big to compile at once. So that means Rosetta is about 3 million lines of code. It's a lot of stuff, and you couldn't, all of that stuff would not fit into memory. So you couldn't actually compile the code. And so what was done is it was split up into libraries that are compiled on top of each other. And when I say on top of each other, this is actually like the other way around. Like basically, like you start with utility, and then you compile the utility library, which is basically generic data structures and helper functions. We will go into this in a little bit. So you compile the first one, the first layer, and then once that's compiled, the next layer, the next library, the numeric layer, depends on it. So it can use those functions, but it's compiled after that. And then you have basic, which is basic infrastructure, options, logging, file handling. Then you have core, and the core of Rosetta is really like atoms, residues, sequences, conformations, anything that has to do with proteins. Then you have the protocols layer on top of that, which is really like protocols. It's like, oh, we're doing docking, we're doing loop modeling, we're doing, you know, flex pep doc, whatever. So all of these pieces together are in the protocols layer, like really what it says, protocols, right? And then you have another one on top of that, which is devel. It's really like experimental code. This is mostly like historic, has been there even from, you know, before we used GitHub. But these are basically the layers. And so when you compile Rosetta, the reason why it takes so long is you start with compiling utility, compiles all of utility, and then after that's done, you start with numeric, and then compiles everything in numeric. Then you build basic on top of it, and so on and so forth. Does that make sense? So, and when you basically link things together, what the compiler really sees, when you link the libraries together, the compiler sees the API. And the API is really like, you imagine the 2 rooms over here. I'm standing over there in where we had lunch, and I'm handing Rocco in here something. And, you know, like, we cannot access anything else, but what we're handing through that doorway is really like what the other libraries can access, if that makes sense. So API is basically function signatures, right? If you're defining a function, these are like the input variables, and this is like what functions return. So this is really like the API. Making sense? Okay, cool. Basically, what I already mentioned, Rosetta is not one monolith. It's a stack of interdependent libraries, and stack because one is compiled after the other. And yeah, each library defines the public API, so basically what other libraries can use. and then the internal implementation details basically what stays private. And so you've seen this in the code. If you have like private member variables, if you have public variables, that's basically what you know, everything that's public is API, and everything internal is what's private and other libraries can't see. And so the build system compiles them separately and then links them together into executables. And those executables could be Rosetta scripts or loop model or docking and so on and so forth. So when you compile Rosetta in your binary directory, you have a ton of executables, right? And so this is what those executables are. So let's see. So yeah, the compiler basically only needs to see the header files to be able to link the libraries together. And the compiler doesn't actually like really need like the details. So basically everything that's in the header file is really like pretty much the API. So quick overview. Again, we've talked about this. So basically the first library is actually objects FCL. That's a very math dependent, you know, library that we're using, or standard library. Then we have utility on top of that, numeric, basic, core, protocols, and devel. And so today we're going to talk about the red things here: utility, numeric, basic, core. Then core is split up into 5 different core levels: core 1, core 2, till core 5. And then protocols, you have a whole bunch of them. So you have 7 different layers, and they're all, you know, this is how they're dependent on each other. And so we're not going to talk about protocols today. We're going to talk about, you know, the ones in red. So this is just a really quick overview of like, you know, what we're going to be talking about today. We have, you know, the utility library, the one that's, you know, compiled first, very useful data structures, very general code, right? So you have like utility vector 1, you'll be using a lot. Utility vector 0 is in there as well. Arrays, IO stream, tags for Rosetta scripts, and then also things like memory management, like heap, and you know, some other things. Numeric, second layer. Generic generic mathematical methods, so that rely on the data structures from utility. So you have, for example, XYZ vectors. You'll be, you know, implementing a lot of XYZ vector ones and stuff like that. Homogeneous transform, we're going to talk about that. You have the functions, XYZ functions, angle functions, interpolation, anything like that. The derivatives, and also, you know, other things. There's a lot of stuff in there. We're only going to be touching things that you will see a lot. Yeah. Basic is the first one that really has like some low-level Rosetta code. The option system is implemented here, and then the tracers, which is basically has to do with like your logging system. Core 1 has the types implemented, and we're going to go about that. And we did talk about graphs yesterday, so graphs are in Core 1 as well. Core 2, you have core IDs, and so we have atom IDs, we have degrees of freedom, we have torsion IDs, then we have core kinematics are here. We are going to be talking about full trees and atom trees later in the afternoon, so we're not going to talk about it in this lecture. But we also have core chemicals, so we have residue types and residue type sets. We have core conformation, so residue and conformation. I'm going to tell you like what the difference between those two is, and then also symmetry information, or symmetry and conformation. So how do they work? So let's go into like a little bit more detail. So again, utility, you know, what we talk about here. So before, I really want to like, because I don't think we've talked about this before, and I don't think it's been part of the homework, like how does memory really work, right? So memory, and I am talking about this simply because in C++, you have to basically manage memory. And so it's kind of like important to at least understand it a little bit, right? So each of those squares over here is an address in your memory. So think of it as like a mailbox, and that's basically your hard drive, right? So and each square has a specific amount of data that it can store, and it's called a bit, right? So you have, it can store either a 1 or a 0. And so, 8 bits is 1 byte, so 1 row, so 8 of those can store 2 to the power of 8 values, so 256 values, right? And so then you have a heap and a stack. Who here has heard about a heap and a stack? A lot of you? Okay, so that's good. So a heap, you can imagine this. I just put a heap of sand here because it's kind of, pretty much what it is. So you allocate memory dynamically. You can allocate it with a variable length, but it is slower because the computer has to figure out where to stick it into your memory, right? And then you have the stack, which means everything is stacked on top of each other. So whatever is pushed onto your data structure last in, first out, right? So it's fixed length allocation. But it's fast to allocate because the computer doesn't have to think about where to stick your data structure onto memory. And so if you want a little bit more detail on that, that's basically here when it comes to like speed, size, how to access it. Stack is automatically cleaned up versus heap is not, things like that. So you can, so you have the detail here. So utility. We have utility vector 1. You've probably heard about that a bunch of times already. And so the T basically stands for a template class. So whether it's utility vector 1 of ints or utility vector 1 of sizes, we call it a utility vector 1 because it indexes from 1, unlike a standard vector. So most of the time you will be using a utility vector 1, which, and standard vector indexes from 0. So yeah, that's basically indexing. And utility vector 1 also asserts the boundary conditions in the operator, the square brackets, in the debug build, whereas standard vector does not. So the standard vector does assert the boundary conditions in its at method, but it's not really used very much. And so assertions are removed in the release builds, so you don't have that much, stuff that scrolls on your screen when you run it, and it's just also faster. So essentially, utility vector 1 derives from standard vector, and it also works basically with all the standard library functions or algorithms, for example, like sort. So you can use sort on utility vector 1. Then you have a fixed size array. So that's basically an array of exactly S elements on the stack. So again, on the stack, rapid allocation, rapid deallocation, but you cannot resize it. So you can't, whereas like utility vector 1, you can push back, another element. You can't do this with a fixed size array because obviously it's fixed. So it indexes from 1, yeah, and then unlike boost arrays, and then also asserts the boundary conditions in its operator, square bracket methods. And it also works with standard library algorithms like sort. Then another one in utility, we have streams. And so utility IO, IZ stream. So that basically means you can read from a regular file or a gzip file. And so you basically initialize a stream with an unzipped file name, for example, example txt. And if it cannot be found, it looks automatically for the gzipped version of it. So that's kind of nice. So you don't have to like give it all the variations of zipping for it to be able to find it. And yeah, and then use this one instead of the if stream. The next one in utility, we have the class tag, which comes from like reference, like obviously you have a reference count. And the tag is really used in Rosetta scripts, right? So the private member variables are basically the name of the tag. You have the map of a standard string and string, basically the options of the tags. And then you have the vector1 of tag OPs that are basically the tags itself. And so the tags are these names in Rosetta scripts. You've probably seen them before, I would imagine. So yeah, so a class tag is implemented in utility. And again, you don't need to like memorize all of that here, what we're going to be talking about. But when I went through bootcamp, I found it incredibly helpful that I've seen this stuff before and that, you know, I could actually go back to the presentations and the lectures where I could be reminded of what we did talk about and you know, so so I hope this is going to be useful. So numeric, yeah, so we have the XYZ vector, has the private member variables, basically XYZ, pretty much position. And it is implemented in core types. So the namespace is core, and there's, you know, the type def numeric XYZ vector is basically the vector. There's lots of useful, you know, operations in there, dot product, cross product, normalization to unit length, like all kinds of things. So I would really recommend like go in there, check it out, look around and like see what's all in there so that next time you know where things are. XYZ matrix. Basically, we know what matrices are. You have all of these, you know, 9 matrix elements. And they can be useful for representing rotation matrices, but then there's also homogeneous transforms as well. And so homogeneous transforms basically means you have, you know, the 9 matrix elements, and then you have another 4th element here, which basically encodes the translation on top of the rotation. So basically you can use homogeneous transforms to do rotations and translations in one. So for example, if you have a frame F, which is basically your matrix, and then you have a local coordinate Q, if you multiply that frame with the local coordinate Q, you're basically ending up in the global coordinate system. And so you can basically use that very easily to go from the local to the global coordinate system back and forth. Now, if you want to compute the local coordinate Q, you basically add the inverse to that, and then you basically end up with your local coordinate. And homogeneous transforms basically, you know, matrices are matrix multiplication for everything. So they're invertible, which means you can compute the inverse very easily to go from global to local coordinate systems. They're also associative, which means you can chain those transformations together. So imagine you're performing a rigid body transformation of one of the chains, and you rotate along the first axis, let's call the axis V by a certain amount, and then you translate along a V prime axis by a certain amount. And then after that, you rotate again after around a new axis, V double prime. And so what that would look like, you would basically have rotation around V, translation around V prime, and rotation about around V double prime. And this is basically your point, and you would run this for all you know, for all i's, for all points in space. Not all points, X, Y, Z, basically. But because it's associative, you can put this together, the RV, everything that's here in blue, into one matrix. So you can basically run the matrix multiplication of the RV, T, V prime, R, V double prime, lump this all together, and then for each point, basically compute just the T times the point I for all I. And then that way, it makes your it makes your math a lot faster. And so this is used, for example, in the matcher protocol. So you can look it up in protocols match and for examples on how to use this. Still with us? Good? Yeah? Okay, cool. So numeric, there's XYZ functions in there, and XYZ functions, you will use that a lot. Anything that has to do with dihedral angles, radian angles, transposing things, this is all in XYZ functions.ah. So I recommend you go check it out because you'll be using it a lot. And yeah, useful, just math. So basic, we have, command line options are there. Let's talk about tracers for a minute. What are tracers? So in your homework, you have, I imagine most likely used standard cout to print something out to the screen. We actually prefer tracers for many things, and here's why. So first of all, they are mutable, basically we can mute them. That's what I mean by that. You can basically mute the tracers. That means in your log file, they don't show up. But if you want them to show up in your log file, if you want to debug something, you can, have them in there. And so basically each tracer, you name them after the file where it lives in. So for example, you can have ones in core chemical, and you would call them core chemical tracers, but you can mute them. So you can basically mute tracers from all kinds of libraries very easily on the command line. Because they're named by where they're coming from, they're also greppable. That means because they print their name at the beginning of each line of output, you can basically have your output run, and then you can say, hey, I'm only looking for the tracers of the e-table. And then that way, you don't have 1,000 lines of output and you need to go through every single one of them, but you know exactly what you're looking for, and that way you can debug things a lot faster. Does that make sense? Okay, so that's what tracers are for. And the way you're using them, so basically the way you're implementing them is you're basically saying thread local static tracer, the capital TR, and then in quotes, your file name. And then if you're using them, you're basically saying tracer, the smaller sign, initializing e-table, or whatever you want to say, and then standard end line. And so that's basically how you'll be using them. So core 1, we've made it to core 1. So there's types in there, there's graphs in there. Types are basically the types that when you call and say there's a size or a real, we're basically telling Rosetta what that means depending on the platform that you're on, depending on the computer that you're on. Obviously, Rosetta runs on, your laptop, your Mac, your cluster, and each platform has a different, how much memory there is, and so basically, we're telling Rosetta, oh, depending on this platform, this is what a size is, or this is what a real is. And so this all lives in core types. Yeah. Now we're in core 2. Okay, we're getting there. Atom IDs and so on. So let's see. So core 2, there's, the key architectural plan. You have a chemical layer, and then you have a confirmation layer on top of that. And what that means is the chemical layer really stores abstract information on atom types. For example, you have the CH2 carbon or residue types. You have like, a generic alanine, right? And then, so that's really, just abstract. And then you have the confirmation layer on top of that, where basically you're storing whatever atom or residue types you have, but are at particular points in space. So now you're actually attaching this to 3 dimensions. And so this is really what the confirmation layer is. So again, remember, if you have a protein and you have a specific confirmation of a protein, that's basically what this is. And so we need to have the chemical layer first because we need to define what the concepts are, and then we can attach, the 3 dimensions to it. So again, in core 2, on the left-hand side, you have the chemical layer. So let's say you have a residue type, and the residue type has, number of atoms and utility vector 1 of atom types, basically the atoms here. And then the confirmation layer has the chemical residue types, the types there, and then also the utility vector 1 of like atoms, basically. So yeah, so this is really, confirmation, and this is chemical. Let's see, and so we have the residue types. They also have like, for hydrogen bond acceptors and donors. Yeah, so that's basically in the residue type, and that's faster to iterate over all the acceptors than to ask every atom a UN acceptor. So you can basically, there's a whole bunch of information stored in the residue type itself to make things faster and easier. Path distance is, for example, the number of chemical bonds separating atom I and J in a residue type, and that's really used in like, calculating Lennard-Jones potentials and Coulombic interactions. So yeah. What else? Ordered atoms. The graph is in here, the residue graph is in here, and then you have ordered atoms for atoms for vertices and bonds for edges. And so there's basically via a vertex descriptor. Oh, never mind, that's the graph. And then ordered atoms, basically you retrieve the vertex descriptor for an atom given its index, and then atom index for the name. So you basically traverse the residue from the residue graph that you're giving it. So again, we have, graphs as data structures. So the atoms would be the vertices, the chemical bonds are basically the edges, and atoms have data to describe them, like names, elements, charges, and so on and so forth. Why do we need a graph for that? Why can't we just iterate over, a list or a vector? Simply because those elements change depending on where you are in space. And so you really need like chemical bonds to, you basically need to traverse the graph and like basically see where they are. So chemical bonds have data to describe them as well. So first, who are they between? So this is handled by the graph. And then obviously you also have like order, the ideal distance, aromaticity, and so on and so forth. So then, let's see, residue type. We have residue connections here. And so that stores information how this residue connects to others. For example, alanine residues has 2 connections, one at the N terminus, one at the C terminus. The same, you basically need to traverse the graph and like basically see where they are. So chemical bonds have data to describe them as well. So first, who are they between? So this is handled by the graph. And then obviously you also have like order, the ideal distance, aromaticity, and so on and so forth. So then, let's see, residue type. We have residue connections here. And so that stores information how this residue connects to others. For example, alanine residues has 2 connections, one at the N terminus, one at the C terminus. The same with the regular cysteine, but then the CYD, basically the one that's in through that is linked basically you have 3 residue connections, and one of them is at the sulfur atom with a regular cysteine. But then the CYD, basically the one that's in through that is linked, basically, you have 3 residue connections, and one of them is at the sulfur atom. Let's see. And then you have the residue type set. And each residue type set must have a unique name in its residue, or each residue type must have a unique name in its residue type set. And that's given by the access pointer. So yeah, and then residue, obviously you have, atoms, and atoms are, described by XYZ coordinates and short type, and then the I guess that's molecular mechanics type. Let's see, and then there's connector map, and this shows how the residue is connected to other residues in the pose. So yeah. And this keeps going. So chi angles, main chain torsions, like all of this is described in the conformation layer and the residue. So this is really stores internal degrees of freedom. Yeah. And then you have the conformation class, so that basically sits on top of that. So you basically is described by, residues. And the conformation does not give out non-const access to its residue. And that is because the conformation lets you see the residues, but it doesn't want you to mess with the full tree and the atom tree that we'll be talking about later today. And let's see. So conformation has degrees of freedom, has torsion angles, has you're able to basically set these from or within the conformation object, so they're accessible. You can set the XYZ coordinates using atom IDs, using torsion IDs, and things like that. And then you have the symmetric conformation, right? And symmetric conformation basically means you have a symmetry info object that describes how the different chains are connected to each other. And that also, in the symmetry info, we basically, and we're actually going to talk about this later today, in the full tree lecture. The symmetry info records dependencies between the residues and between jumps in the full tree. And what jumps in the full tree are is something that you're going to be learning today. So basically, there is a way where we can describe how the different chains in symmetric conformations are connected to each other, and what's flexible and what's not. So that's all in core conformation symmetry info. And that's it for this one. Any questions? Yes.
So in my understanding, X coordination and internal coordination are safe in the object. So if
Are what?
XYZ coordination, Cartesian coordination and internal coordination things are safe at the same time. So if we perturb in using internal coordination, then does it update XYZ coordination by automatically, or?
I mean, like the information is really stored in the pose, and in the pose, it's internal coordinate system. So I don't know whether it stores
It stores both the internal coordinates and the Cartesian coordinates, and that's really the main job of the conformation class, is to sort of keep those two systems in check or coordinated with each other. So basically, what it has is there's information about which sort of state is the most up to date, and then automatically when you go to the next, you try and access an internal coordinate, it'll automatically update everything and recalculate if it needs to. And so that's really a lot of the complexity of the conformation class, is to encapsulate all that information and to provide a transparent interface such that you don't have to worry about converting between internal coordinates and the Cartesian coordinates. The confirmation class takes care of that and sort of hides that all within that class structure. And that's, again, that's the main goal of the confirmation class, is to hide all that information from you.
But wouldn't you say that the XYZ coordinates, that basically the internal coordinates are always automatically updated and the XYZ coordinates are lazily updated?
System as far as keeping track of what's up to date and what's not.
Okay.
And automatically, if one's not up to date, whenever you access it, it recalculates as needed.
Okay. Okay. Makes sense?
Yeah, that makes sense.
Thank you. Any other questions? Okay.